And we will start the last session of today. And our first speaker today will be Anna Stachto, and she will tell us about the model for FL and F2 structure functions at low Q square and X values. Anya, you have 17 minutes for your talk. I will remind you 2 minutes before the time ends. Please start. Thank you.
Thank you, Kasia. Can you see my slide?
Yes, and we can hear you very well.
All right, thank you very much. Thank you very much for allowing me to give this talk. This is a revisiting of a model for longitudinal structure function at low Q square. This is a model that we did many years ago, and we are now looking at it again in the context of new data and in order to make predictions for the IC. So this work is done in collaboration with Barbara Badelek, and it's still much in progress. So first I will start with the motivation for actually looking at the model that goes into the low Q square region, which essentially, aside from theoretical interest, is also a practical interest because it's necessary for the DIS radiative corrections and essential for EIC. The model, I will remind that the construction of the model, which is based on KT factorization plus modeling of the higher twist contribution. I will show you some results on X and Q square, generic Q square and X behavior, and then going to show you some comparison with the JLab, SLUG, and HERA data and summarize. So as a motivation, what we are interested in is, of course, this extraction of one photon cross section from the measurement, but it requires the knowledge of all kinds of radiative corrections, both on the lepton side and on the hadron side, and usually this is taken into account by a radiative correction factor, which is essentially the ratio of the one photon cross section to the measured cross section. And the examples of schemes for the radiative corrections are, for example, the famous mod science scheme, which essentially takes into account the radiation from the lepton vertex, and the Dubna scheme that includes the hadron current corrections within the quark parton model. And in this very nice paper, the comparison of different schemes was performed. Now, the point is that if one looks at the Q square and nu plane, the energy of the photon plane, then this is the plot taken from this reference. Then if one measures one performs particular measurement at point A, which is at some value of Q square and nu, then everything that is in this triangle stems from the radiative tails, and they contribute to the cross section at this point. So one needs to have a knowledge about the structure functions from in this triangles. So in other words, one needs the following input where for x's that are essentially bigger than the x measured, but in a range of Q square that essentially goes down to essentially 0. And so we need both structure functions F2 and FL, or FL or the ratio R. And so this is the motivation. Now, unlike F2, where there are lots of data and it's easier to constrain the low Q square behavior, the situation with FL is different, and the amount of data is much less. Here are HERA data, here are the CERN NMC and BCDMS data, and here we have SLUG together with the JLab. So it's really the JLab that goes to the lowest Q square, but it's also at the highest X. So the model that we are kind of refreshing is, so here are the basic ingredients of this model. And the motivation is not to have, one could also have some parameterization, but we want to have a bit more physically motivated model with the least number of free parameters as possible. And we use the KT factorization formula with the off-shell gluon density. Then we have some parameterization of this unintegrated gluon distribution, which in this particular case, we construct from the standard DGLAB collinear distribution. And then we perform the extrapolation to the values of Q square by essentially performing some procedure where we separate the regions of the quark transverse momenta into low and high regions, and we treat this region from the low quark transverse momenta. This becomes a higher twist, and we match this to the soft contribution from the F2 structure functions. The original model was published many years ago, and we are looking what has I mean, how the data change and how to improve it. So this is here you see more details. So this is the KT factorization, which is most appropriate for small x. And it's a convolution of the photon gluon impact factor. So this would appear here in this formula, and the unintegrated gluon density, this little f, and there is an expression for this photon gluon impact factor shown in here, and there are explicit integrations of the gluon transverse momentum and the quark transverse momentum. This formula contains so-called exact kinematics here in the form of this delta function. The exact kinematics of this box. Now, the model for the higher twist is very simple. It's just one is saying, well, let's imagine that so there are integrals over these quark transverse momenta that are extending to small and high values of KT. So for large quark transverse momenta, we essentially keep the perturbative formula, but for the small quark transverse momenta, we assume that there is, first of all, on-shell approximation, so the gluon is on-shell, and then we say that the alpha s times the gluon density is essentially some constant, so there is some this is going to be extension to the soft region, and then the expression for the higher twist contribution, so from this contribution of low quark transverse momenta, has a compact form, and you can see indeed that this is a higher twist because it goes like 1 over q square when q square goes to infinity, right? So there's q to the 4th, and then there is this denominator to power 4, so this is going to go like q to the 4 divided by q to the 8, so 1 over q square. And then vanishes like q to the 4 when q square goes to 0. So like you would expect for FL to vanish because the cross section vanishes like q square. So then this constant A is not a free parameter. So we essentially estimated from F2, assuming that non-perturbative contribution to F2 also comes from low quark transverse momenta. So we take the expression in terms of KT factorization for F2 or F transverse, and then we integrate over the low quark transverse momentum again. Again, we assume that the same alpha s times the gluon is a constant, and then we get some contribution from this non-perturbative region, which has compact expression. And we interpret this as a soft contribution that was essentially found from a separate analysis to be about 0.4. So this is how we determine the higher twist contribution. And then the last few things, ingredients of the models, is the unintegrated gluon density. Now, in principle here, there are numerous options that one can put in because, of course, one can use either BFKL or some saturation model or the DGLAB motivated KMR model. We have used something very simple in terms of we just took the collinear density and performed the logarithmic derivative. And it turns out that in the low Q square region, there is not much sensitivity to it because the perturbative contribution is, of course, not large, but nevertheless, one can explore different scenarios here. This cutoff turns out to be somewhere between 0.8 and 1.5. The results are not very sensitive to it, somewhat sensitive, but not too much. And we use the following masses of quarks, which you see the constituent quark masses for the light set of quarks. So what are how the FL looks like and how these different components look like when we go to particularly to low Q-score regions. So here you see the comparison of old calculations. So the code that has been publicly available was actually based on GRV94 versus the updated CT14. And you see the differences between the old and new, of course, in the large Q-score region. And this for the smallest X, not so much, of course, for the low Q-score region, where essentially everything is set to the soft contributions, and that was set by the data, so it doesn't really change here much. Here is again the comparison of what was available before and now. Again, not so much in the difference in the large, in the small Q-score region, and some difference in the low X and the higher Q-score region. So obviously this GRV94 had a very steep X dependence as compared to the newest parameterizations. In terms of the different components, so obviously the perturbative component dominates at large Q-square and low X, like we all know, but the higher twist is significant, like we would expect at low to moderate Q-square. So in each of these plots, you see this higher twist, which has this characteristic behavior. So it vanishes as Q to the fourth at low Q-score, and then it vanishes like 1 over Q-score at high Q-score. So it's a genuinely higher twist contribution, but its dominance is mostly at large X. Similarly, in this plot, you see the higher twist here, which is flat in all these plots because it has this soft Pomeron-like behavior. And then any type of growth is, of course, due to the perturbative component. So these are the, this is just general behavior. Now, as far as the data are concerned, so this is the comparison with the H1 data plotted here. And of course, these are measurements which are at different X's and different Q-squares. So Q-square is shown here. So this is not a low Q-square measurement. The lowest is 1.5. The calculation goes through the data. It's not a surprise. I mean, in this region, this is based on the perturbative components. So we should expect it to be consistent with the data by definition. And this region will be most sensitive to PDFs, so we can fix it by tuning the PDFs here. For the low Q-square data, so these are the lowest Q-square data available, and they come from JLab and SLAC. And so here you have 0.3, 0.5, 0.8, and 1. This is the model, and these are current data. And as it stands now, the model, as you see, underestimates the data. And this is hardly surprising. The model was constructed for low X. So in some sense, it's the region which is beyond the applicability of this model. So this is what we have now. And here you see the black points are the new JLab data. This the SLAC is blue and green is the older data. There's one small caveat. I mean, the SLAC and old JLab data are actually rebined with some models assumption. We would not expect that this rebinning would change much of the data, but it would be nice to have the raw data for comparison. So this leads me to my summary. So the F2 and FL in the low Q-score region are necessary, not only, I mean, the knowledge about them is not only interesting from the theoretical point of view, but necessary for radiative corrections. And this is going to be crucial for EIC precision measurement. What we are doing is essentially revisiting the old model that we had for low Q square based on KT factorization and higher twist. In the kinematic region of the model where low X and low Q square, we don't have much of the dependencies on PDFs. The model describes HERA very well, and it's not surprising. With the lowest Q square data, the model is underestimating the data, but the data are at large X. So on one hand, that's not too bad in a sense that this is beyond the region of applicability of the model. On the other hand, one would probably like to have something that describes these data as well. For the outlook, we want to look at other models specifically of the unintegrated densities, which are maybe low X specific, other sources of higher twists, and particularly those who would contribute at large X, and also include the target mass corrections. So thank you very much for your attention.
Thank you, Anya, very much for a very interesting talk and also for being perfectly in time. So now I open the discussion. Are there any questions? Please raise your hand here on Zoom if you want to ask a question. Okay, then I don't see any hands, but I have a question. So in the second last point in your summary, you say that the JLab data don't agree very well because it's large X. And do you have any ideas how to, improve the situation?
So, I mean, I have some vague ideas, but it's nothing that I would like to perhaps commit to at this point. I mean, you see here the quality. I mean, so the quality data is what it is, right? And then, but there is clearly a shift. I think that we are missing some other, sources of the higher twists here. And I looked at some of our other models that I calculated FL in some other approach, in a similar approach, but somewhat differently, and I got a higher results. But so I have some, I wouldn't commit to any specific,
Okay, so we will wait for DIS next year, hopefully not online anymore, and then you will show us better comparison.
Yeah, I hope so, yes.
Okay, I see that Krzysztof wants to ask a question. Please go on.
Anu, what's the motivation for the choice of the parton distributions? And the second question is, do you believe that you can apply this distribution, that they are meaningful in the region of, let's say, 0.3 GeV square?
Okay, so we are, I mean, so in terms of the parton distributions, no, I mean, that's the whole point, right? I mean, we are basically cutting them off at, so that there are actually two cutoffs here. One is a cutoff on the quark transverse momenta, and the other is a cutoff on KT, which I haven't essentially mentioned, but yeah, I mean, it's essentially the parton distributions are applied where they should be applied in the perturbative region, so there is no issue there. Your second question about the choice of F, I mean, here, I mean, we don't have to really stick to this this prescription, and this is why we can use some other prescriptions, and in particular, in the paper with that we have in common, right? We have computed FL in a somewhat different formalism, where we had the resummation at small x. So for example, that could maybe be a bit more appropriate. This will not solve the large X problem though, right? So there is another source of physics at large X.
Okay, I see Barbara raised her hand.
Yes, I wish to comment on the two questions which arose here. First, the applicability of the parton distribution here. As Anna just said, it is at the mostly perturbative region, but the problem is that in this model, we are sort of shifting the position in Q square at which we take the parton distributions. That we show the contribution of all sorts of contributions here at small Q square doesn't mean that we are actually calculating those contributions at this particular Q square. It's one of the elements of the models that we are shifting both Q square and X in a proper way. And then the first question of Katarina, how can we help the comparison with the data? That is this, as Anna said, the small caveat here, that actually we could not find raw measured data from old experiments. We asked for help, we asked our colleagues from Jefferson Lab for help, and they were very kind to share with us their database. However, this database has been modified, not by us, by those who performed the analysis earlier. They wanted to have the measurements in particular bins, let's say bins of X or bins of Q square, and they have earlier in time rebinned them appropriately so as they were convenient to their analysis. We still try to somehow find the real data. They are very difficult to dig up because they are normally shown in old PhD theses, not always easy to find. So this comparison with data might be slightly, yes, in here, in those bins of Q square here, they might slightly improve, however, not in a very critical way. These rebinning effects are probably extremely small, but nevertheless, one has to remember this.
Okay, thank you very much for the interesting discussion. And now we will go to the next talk. Anya, could you unshare? Yes, we will have now Sasha Glazov telling us about Defiducialization. I cannot even pronounce the name. Sasha, can you share your slides and your title?
Yeah, sure.
Please?
All right.
You have 17 minutes for your talk. I will remind you 2 minutes before it ends. Thank you.
Okay. Okay, so yeah, this is defiducialization, and yeah, this is a well, the word is of course difficult to pronounce. I myself cannot really pronounce it. Yeah, so the idea is to try to improve the way we perform measurements such that we can perform more exact comparisons to fixed order predictions. Yeah, so just a few words of the motivations. Obviously, if we want to determine PDFs with high accuracy, we need both accurate predictions and the data. And for the data, there are, of course, limitations. So we cannot measure in the regions where we have no detector. So we have to apply cuts on which are so-called diffidential cuts. In particular, for WZ production, typical cuts would be on PT, which is a trigger requirement, and on the pseudo rapidity of the lepton, which would be acceptance of the calorimeter. And so if we do this, we still can get extremely precise measurements, which are sometimes better than % accuracy, sometimes 0.5% accuracy. So this we reach already with 7TV data. On the other hand, if we look at next to next leading order theoretical predictions, and we start comparing in the fiducial phase space, we may see that there are differences, and there is a very recent analysis of that on the archive. And yeah, so this probably is related to the way subtraction scheme is performed. Subtraction is performed, but nonetheless, there is a problem. Okay, and the problem is probably coming from the fact that fixed order predictions are perhaps not optimal if you have fiducial cuts, since fiducial cuts shape PT distribution, and fixed order predictions are good only if you integrate over PT. Okay, so it would be very beneficial, instead of comparing the fiducial phase space, is to perform comparison of the full phase space. In this case, there will be a better match between data and theory. Obviously, this type of problem that there is a mismatch between data, what you can do the best in data and theory, is an old story. So we had similar with jets, say, and we moved from quants to anti-KT, but now we also have some similar issues. So this is okay. Same story, but of course different situation for drill. Yeah. So in principle, there are 3 ways to improve the situation, and so roughly the first one would be to directly extrapolate the measurement from the fiducial to the full phase space. So this was done, for example, in the Atlas analysis listed here. In fact, you can do it with very little uncertainties, and this is following more or less the same ideas as I will discuss today. The second approach would be to separate regions which are having low acceptance and to perform comparisons to the fixed order QCD only for high acceptance regions. And this is actually again possible, and it's probably almost giving you the whole solution, because exactly these high acceptance regions are also accurate in data, more accurate in data compared to the rest. And finally, there is this solution that is to correct fiducial measurements, which is provided differentiating the boson PT to the full phase space. Okay, so first, this idea to do the separation of low acceptance regions compared to high acceptance. This is okay. The first thing measurement which was performed like that is a triple differential measurement of the earlier cross-section performed by Atlas, so which is binned in invariant mass, in rapidity, and cos theta angle and the column superframe. And so this is 3 slices in the invariant mass shown here, and it's a function of rapidity for different cos theta bins. And so just to say that there are, of course, very many features that you can observe here. For example, forward-backward asymmetry, which is changing sign as you move in the mass. But what's also interesting is if we look at the bins corresponding to smaller cos theta, you see that they remain flat up to very large values of the rapidity, and then they only start to cut off. While if you go to large cos theta, you straight away start to drop. And this is actually the impact of the fiducial cuts. This is just the fact that in this case the leptons go forward backward, and the eta requirement start to kill the acceptances as you go higher in rapidity. Okay, so right, indeed, if you compute acceptance for this measurement so in some way, so this was performed in this physics analysis, and so this was performed using an analog jet. You indeed see that for central, for small cos theta and central rapidities, the acceptance for large invariant masses very often is close to unity. So it's above 95% for more than 50% of the bins, and exactly in these bins the measurement is most accurate. And if you restrict your analysis to these bins, as was done by recent MSHD fit, you can immediately see that the fit quality for an lower fit becomes quite acceptable, and despite the fact that the accuracy of this data is also extremely high, 0.5% level of uncertainties. Okay, so this is one approach. The other approach is this defiducialization, and just to give you an idea what's going on here. So it's all starting from the factorization of the cross-section and QCD. So we have first the production of the Z boson, which decays. And in principle, the kinematics of the final state leptons is actually fully determined given rapidity, invariant mass, PT, and polarization. And polarization is given by essentially 8 coefficients. And in fact, out of all coefficients, the most important one is A0. The rest is not so important for the fiducial cuts we have. And the idea behind all this is that the polarization can be computed at fixed order for this given rapidity, invariant mass, and PT. And therefore, the acceptance can be also determined with fixed order at high accuracy. So we can do it up to next to leading order if we use T plus jet from an low jet. Okay, so this can work fine. Of course, there are electroweak corrections which actually break this vectorization. So they can be incorporated in the full procedure, but also they are small in the peak region. So we heard that the photon induced can be large from Lucien, but in practice, there are cuts against that, and it's normally very small. Okay, right. So then the basic idea would be to perform comparison of in the full phase space where we integrate over the PT, and compared to the fiducial comparison where we correct the theory effectively by this acceptance. Okay, so in the case of this fiducial comparison, we just would perform integration and PT straight away in the data. And in our case, which is advocated here, we would first determine acceptance based on the theory, correct the data, and then integrate. So the advantage here that, yeah, so this integration doesn't require exact knowledge of the PT spectrum to integrate over it. While here, if the acceptance does depend on PT, we do need to model PT spectrum, and fixed order predictions don't always do that properly. Okay, so that's the idea. Let's try it. So the exercise is done using Atlas ZPT data measured at 8 TV. So publication a while ago. So details of this measurement are not important, but there is one data set which is binned in PT and rapidity for the peak region. And the binning is sufficiently fine such that we have a meaningful rapidity dependence and also rather small PT bins such that the correction, so acceptance variation within the bin should not be very important. And as usual, this is in fiducial phase space with PT and rapidity cuts. Okay, so let's start straight away with the computation of the acceptance as a function of PT for this 6 rapidity bins. And this is done using MCFM. So interface to Apple Grid, that's why it's an earlier version. This is interesting because you want to look at the PDF dependence. And yes, this is Z plus jet with PT jet of 1 GV. So obviously MCFM, this and low prediction for this low PT would be totally wrong in terms of rates. But we don't care about rates, right? So we care about the ratio of what is accepted by fiducial cuts compared to everything. And this should be fine because we've been finally in PT, and the polarization is actually described by the fixed order. Okay, and right, so we can even perform calculation at leading order. It looks that next to leading order correction is relatively small. So this is what you see here. So these are two predictions which are leading order and next leading order compared to each other. And you do see that acceptance is a function of PT, so it's not flat. If it would be flat, there would be no problem on fiducial cuts. So that's what the two integrations would be equivalent. But it's also becoming more flat for certain rapidity regions. So in this range, there should be no difference in the two approaches. But it should be more important for low rapidity and maybe again for higher rapidity. So we will see in the results if it's true. Yeah, so to see the effect of higher orders, we can look at the delta. So it's n low minus a low minus divided by a low minus 1. And indeed, you see the corrections are at low PT are tiny, and at higher PT they are becoming larger, but still they are below 0.5%. And this is actually expected. So, right. And based on that, we of course, an issue that you cannot do up to PT of 0. So you have to do something, and there is an approximation to treat this bin. Okay, so then we can also compute PDF uncertainties on this acceptance factor and compare and perform scale variation. So one can do traditional scale variation, or one can do more conservative scale variation, decorrelating certain parts. So this is what I show in this particular slide is a traditional scale variation compared to PDFs. And what one sees is that the PDFs are becoming quite large for large rapidity. Becoming quite large means it's 0.1%. So it's still pretty small. But this is also clear that they are at the edge of the phase space. So the bin is, if you look at the absolute value of the acceptance is quite low, below 20%. Okay, so all uncertainty seems to be under control. So now let's continue with the exercise. So first we correct the fiducial data in PT to the full phase space, and we perform comparison to the NLO Z plus Z predictions in terms of the ratio of this full phase space to the first bin. So this is just by construction at unity, and so just essentially probe differential PT and rapidity dependence normalized to this bin. And it looks like the first order things are described. So this is already quite interesting piece of information. So it could be also important for things like W mass measurement, because there, of course, we have different fiducial cuts, and so perhaps comparisons should be performed in the full phase space. Okay, but nonetheless, the more interesting part is what happens into the rapidity distribution when we integrate over PT. Okay, so here we perform the integration, but first we just look at the uncertainties which are coming from this procedure. So we see that the data uncertainties are slightly worse compared to our measurements, but still they are at the order of so below 1%, so 0.6%. And so this is all dominated by systematic statistics is 0.1%. And if you look at this acceptance correction uncertainty, it's comparable to statistical uncertainty, so much smaller compared to the total experimental uncertainty. Okay, so now we can perform a comparison of this data to predictions computed at next to leading order. So the flavor of this next to leading order computation is MCFM version 9 with subtraction scheme used there, but for full phase space it shouldn't matter. So they are all equivalent. And yeah, so you see comparison to CT14 in Atlas EPWZ 16 sets. So the features of these two sets is the Atlas set has a very large strange component. We know these data are sensitive to the strangeness, and CT14 has a moderate strangeness, but we also see this normalization issue, which is actually also known.
You have 2 minutes left.
Yeah. Okay. All right. So it's easier to perform comparisons in terms of ratios, and the nice feature about ratios that we can also do on the same plot put the ratio for this full phase space comparison, but also we can do the same for the fiducial phase space. And let's just focus on CT14. So immediately one sees that in the full phase space, the ratio gets flatter, so there is a still normalization issue, but otherwise the rapidity dependence is reduced. Well, there is a sizable dependence for the fiducial. So the tension between CT14 and the data is reduced if we do this defiducialization. Okay, so it's also, of course, interesting to compare to more recent analysis. So CT18, they have a few sets, including also 7 TV Atlas data with enhanced strangeness. So, for example, this is a comparison of this RS ratio of the strange over light C, and this set which contains Atlas data has enhanced strangeness. This is Atlas 7 TV data. All right, so now we can compare this full phase space ratios. And so the CT18 is actually behaving similar to CT14. Not perfect, but if you look at CT18Z and A, they are basically flat. So the conclusion from that, the Atlas 8TV and 7TV data are very consistent in terms of the preference for the strangeness. Yeah. So this is essentially all. And yeah, just to summarize that, so there's a prescription how one can transform fiducial measurement to the full phase space as for the Drell-Yan production, provided that one of the dimensions of the measurement is in PT. So it's tested. So it looks like acceptance correction uncertainty is subleading compared to experimental. It brings some significant differences, at least for MCFM predictions. And yes, with full phase space results seems to be more compatible with CT14 and in perfect agreement with CT18A and CT18Z PDF predictions. Thank you.
Thank you, Sasha, very much for interesting talk and also staying in time. And I am opening discussion. Are there any questions to the talk? Please raise your hand. Okay, Mandy.
Sasha, hi. Given that the 8TV data, you can get it in these with the high acceptance, 95% acceptance. Would you think that using those 8TV data with the high acceptance was more reliable in PDF fits than using the previous 7TV data?
It is probably, right. This is back to this original discussion. Yeah, so I mean, the accuracy of this data is extremely high. The ratio, you also can see it. And right, I didn't, so the chi-square per degrees of freedom in this MSHT 20 feet is pretty reasonable.
Yeah, I mean, it's nice that in any case it seems to be more or less consistent with the 7TV data, but in view of what you're saying about the sensitivity to fiducial cuts, that is far less in the 8TV, so one could really recommend it.
Right. Yeah. Yes, I would say so. Yeah.
Okay, Christopher, please.
Hello, thanks. I have a comment on slide 4. The previous slide, yes. So I think you said that there are differences up to 2% at next to leading order. And are you thinking in those, with this comment, for example, in the larger differences that you can see, for example, in the slice from 66 to 80? For the cosine from -1 to -7. So the first, if you go up with the cursor from -1 to -7, and that the last 2 bins, do you mean those? Because because for those, the leading order is actually 0.
Exactly.
And that's actually the reason why there's such a large difference.
Yes, agree. I mean, so I was very brief on this first part. So yeah, so these are these 2 bins, right? There is a huge difference between predictions and the data, but the reason is indeed leading order is totally 0. So you totally rely on the modeling of the, I mean, so these are showing up only next to leading order. So with the recoiling system, and if it's not modeled well, you cannot model these bins. Yeah, yes. But what I was talking, so for these bins, it's okay. If you integrate over everything, contribution from these bins is relatively moderate, of course, right? But but still there. So if you go to, so here you see huge 20% discrepancy. Obviously, if you integrate, it will be much smaller. So when we talk about sub% level, but still, this is the level of accuracy.
Okay, very good. Then we will go now to the next talk. We will have Thomas Boettcher telling us about PDFs and QCD effects in the forward region of the PP collision. Please, Thomas, Sasha, could you unshare, please?
Just a second, I have issues. Okay.
Okay,
yes.
Very good. Thomas, please share your slides with us.
All right. Can everyone hear me okay?
We can hear you and see your slides very well. Please start. You have 17 minutes. I will remind you 2 minutes before the time ends.
Excellent, thank you. So my name is Tom Boettcher, and I'm going to talk about the work we've been doing on probing proton PDFs at high X with LHCb. So first, I want to talk about the LHCb data that's actually used in PDF fits, and a couple of other measurements that LHCb has performed that are not used in PDF fits, but can also tell us something about the proton structure at high X. And then I want to talk about how we are studying PDFs with heavy flavor jets at LHCb, and finally, how we can use that machinery to search for intrinsic charm. So to understand why we're interested in studying PDFs at LHCb, we have to start with the detector. So LHCb is an experiment that was designed to study B physics at the LHC, and it is the forward spectrometer covering the region of eta from 2 to 5. And so it includes a tracking system, including this high precision vertex locator called the VALO. It also includes a calorimetry system that includes an electromagnetic and hadronic calorimeter, 2 rich detectors for particle ID, and a muon system. And so while this is an experiment that's designed to study B physics at the LHC, it really serves as a general purpose detector in the forward region. In addition, unique to the LHC, LHCb can inject this VALO region with gas and operate as a fixed target experiment through the SMOG system. So because LHCb is in the forward region, we are always probing the interaction of partons with very low X and very high X. And so in addition to this, in the fixed target configuration, we become sensitive to even higher X. And so what I'm going to focus on today is this high X, high Q squared regime at LHCb. So now I want to present the data that's actually used in PDF fits. So LHCb has performed measurements of Z and W boson production, and these are now used in all of the state-of-the-art major PDF fits, CT18 and in PDF 3.1 and MSHT 20. And so you can see the tree level diagrams here on the right. We are really probing the PDFs at the Q squared equal to the vector boson mass squared. That's this region I've highlighted here. And as you change the rapidity of the Z or the W, you probe a different region of X. So here are examples of results of LHCb's W and Z production measurements. So these plots show Z and W production at 8 TeV. And these are both in the muon channel, so Z to mu mu and W to mu nu. So the left shows the rapidity distribution of Z bosons at LHCb, and the right plot shows the pseudo rapidity distribution of muons from W bosons. And so the orange here shows the W plus, and the blue shows the W minus. And in addition to these 8 TeV muon measurements, LHCb has also measured this Z and W production at 7 TeV in both the muon and electron channels. So what effect does this have on parton distributions? So these plots are produced by NNPDF 3.1. And so this shows a comparison of the nominal NNPDF 3.1 fit with the NNPDF 3.1 fit with no LHCb data included. And so this red hatched region is the ratio of the default fit to the no LHCb fit. And so we can see for the down quark PDF, this causes a roughly 1 sigma change in this region above about 0.2, X of 0.2. In addition, in PDF 3.1 was the first general purpose PDF fit to independently fit the charm PDF. And so you can see that LHCb provides some strong constraints on the charm PDF at X above X of about 0.1. And so in general, current LHCb data provides powerful constraints on the quark PDFs at high X. So in addition to these measurements of Z and W production, LHCb has also measured Z to mu mu and Z to EE at 13 TeV. So this is the Z rapidity distribution measured using 2015 data. And this data is now used in the CT18 PDF fit. And so the orange shows the muon channel and the blue shows the electron channel. In addition, LHCb has measured Z to tau tau, both 7 and 8 TeV, and this provides a nice test of lepton universality. And so you can see that the Z to tau tau, mu mu, and EE measurements all agree nicely. LHCb has also measured W and Z production in association with jets. And so this plot on the left shows how we measure the W boson yield. So we use this isolation variable, which is the ratio of the PT of the muon to the PT of the jet that the muon is clustered into. And you can see that W bosons tend to be very isolated. And so this lets us measure our W plus jet yield. And then the results are shown on the right. So these theory predictions, the scale uncertainties are shown in these dark black bars, and the total uncertainties are shown in the light gray. And so to minimize these scale uncertainties, we can construct these asymmetries and ratios. And so you can see in this bottom panel, for example, is the measurement of the W charge asymmetry. And there's some tension between predictions and data. And so with a full run-3 measurement of this W plus jet, in particular, this W charge asymmetry, we expect to be sensitive to quark PDFs at X above about 0.5. So now I want to talk about how we are studying PDFs with heavy flavor jets. So LHCb, because it is a purpose-built B physics experiment, has excellent vertex resolution, and this allows us to tag both B jets and charm jets using secondary vertices. And so we do this with 2 boosted decision trees, one that separates heavy flavor jets from light quark jets and gluon jets, and another that separates beauty and charm jets. And so at this working point of with a mistag probability of 0.3%, which is very low, we tag B jets with an efficiency of about 65% and C jets with an efficiency of about 25%. And so as a nice demonstration of this, we've measured Z to BB bar. And so you can see there's this nice Z peak in the dijet mass distribution of 2 jets I tagged as B jets. So we've used this machinery to measure W production in association with charm, and so this and beauty, and so this provides sensitivity to the strange quark PDFs and the B quark PDFs. And so in each bin of muon isolation, we extract the heavy flavor yield using fits to these isolation BBT distributions, and then we use this isolation variable to extract our W plus jet yield. The results are summarized in this plot on the right. In particular, I want to draw your attention to the W plus charm asymmetry in 8 TeV. So this shows about a 2 sigma tension between the theory and experimental result, and so this could be an indication of some S bar asymmetry in the proton PDF. Another nice thing you can do with heavy flavor tagging is measure top production. So this will be sensitive to the gluon PDF of very high X, and so this LHCb has produced a number of top production measurements. So this particular measurement uses the muon electron B jet final state. And this is a very pure channel. So this plot has 44 events in it and an expectation of about 6 background events. And the results are shown on the right. So this top panel shows the cross-section in LHCb acceptance, and the bottom panel shows the cross-section extrapolated to the full phase space. And so in these results, the systematic and statistical uncertainties are comparable, and the systematics are dominated by our BJet tagging efficiency. So now I want to talk about how we use this machinery to look for intrinsic charm. So most PDF fits assume that charm is generated perturbatively at a scale starting at the charm mass. And so this is what we would call extrinsic charm. So this is via just the D-glap evolution. A gluon is radiated and splits into a CC bar pair that's short-lived. But there's also the possibility that there's a long-lived intrinsic charm component to the proton's wave function. So this would imply at a scale of the charm mass that some fraction of the proton's momentum is carried by charm quarks, and so this is expressed with this intrinsic charm magnitude. And so CT14 has provided PDF sets that assume a few different models of intrinsic charm. So there are two classes, the BHPS and C models. The BHPS models assume a valence-like shape for the charm content, and the C models assume that it has the same shape as the other C quarks. So NNPDF 3.1 was the first general purpose PDF set to independently fit the charm quark PDF, and so it favors this valence-like intrinsic charm component with a magnitude of about 0.4 plus minus 0.4%. So you can see this in this plot on the right. There's this nice bump at high X with large uncertainties. So at LHCb, we have tried to probe intrinsic charm using fixed target charm production. So this is using these.
Just invited me to meet him for a
Okay, that's fine.
I'll be back in half an hour.
Yeah.
Okay. So this is a fixed target charm production. So this is using the smog system. We've measured this in both proton helium and proton argon. And so if this probes the PDFs at low Q squared and high X. And so if there's intrinsic charm, we expect an excess in these most backwards rapidity bends. And this is not what we see. So there's no evidence for significant intrinsic charm in this data. However, this low Q squared fixed target charm production data is complicated to interpret theoretically, and so historically has usually been omitted from PDF fits. So we'd like to measure this with complementary observable. And so what we'd like to do is measure Z production in association with a charm jet. And so this is sort of an ideal probe of intrinsic charm because it is at very high Q squared because of the Z, and because we were measuring it at LHCb, we were always probing a high X and a low X parton. So here are results we expect from run 2 and run 3. So we plan to measure the ratio of Z plus charm over Z plus jet differential cross sections in the rapidity of the Z boson. And so these points here show expected values from different intrinsic charm models, and the error bars show the expected experimental uncertainties. So in run 2, this measurement's currently in progress, and we expect to be sensitive to valence-like intrinsic charm down to about 1%. Things become a lot more interesting in run 3, where we expect to be sensitive to valence-like intrinsic charm down to 0.3%. And so this is interesting because this is the value favored by the NNPDF 3.1 bit. So in summary, LHCb data places strong constraints on the quark PDFs at high X, and LHCb has also produced other measurements that can tell us something about the high X structure of the proton. In particular, we're very excited at the possibility that we'll be able to rule out or observe valence-like intrinsic charm at the level of 1% in run 2 and 0.3% in run 3. Thank you.
Thank you very much, Tom. It was extremely interesting, the summary of results, especially about the intrinsic charm. And you also stay in time. So the speakers in this session are absolutely perfect. Are there any questions? Robert, I see your raised hand.
Yes, this asymmetry for the W plus charm. So I can't figure out immediately which direction you would want your charm, your strangeness asymmetry to be. But of course, there are PDFs that do have asymmetries between S and S bar. So I assume you've not actually tried with any of those.
Yeah, so we have looked at this in some phenomenology studies at some point. I'd have to dig them up, and yeah, I'm not sure either which way this would indicate.
Okay, but as I said, simply the comment that it is something where there will be, in principle, predictions for this, which will certainly test whether it's in the right direction for what those PDFs that have S not equal to S bar actually say.
Yes, and so these PDFs of allowable strange asymmetry go in both directions.
Okay, are there any other questions? I don't see any hand, but I have a question. So I think it's on slide 17 when you show this intrinsic charm, this measurement here, exactly. So if I understood correctly, you expect some deviations or some effects at very low Y, right? So around minus this first left beam. But that is, I mean, you said you see no evidence. So what kind of, here there is a difference, right, from one. What kind of what size of a difference you actually expect to fit the intrinsic charm predictions, if you say that this is not really big enough? Just
yes. Curious. So we would expect an excess in this most backwards bin, and instead we see a deficit. I think there are a lot of caveats with this data in general. So in general, the theory predictions shown, these Hilak-Onia theory predictions, don't describe this data set very well. So this is one of the reasons.
Okay, I missed that you were expecting them larger, not small.
Yes.
Okay, good. But still, it's very interesting, and I'm looking forward to some new results. Okay, I don't see any more hands, so we will continue with the next speaker. Tom, if you could unshare your slides, and our next speaker will be James Ferrando, who will tell us about the determination of PDF using Atlas data. James, could you share your slides, please?
Yep, can you hear me okay?
I can hear you very well, and I can see your slides also. So please start. You have 7 minutes. I will remind you 2 minutes before they end.
Okay, great. Thanks. So it's always a pleasure to speak at DIS and an honor to represent Atlas, of course. So in this talk, I will present the most recent determination of PDFs that we've done at Atlas. It's just in the archive in January, and this extraction is using inclusive WZ and WZ plus Chet's data sets from the LHC Run 1 data, together with HERA combined data. Okay, I guess to this audience is fairly clear that PDFs are basically what affect your rapidity, mass, and charge asymmetry of your final state system and the total cross-section, and that you can generally get these in Monte Carlos next to leading order in QCD, and then fixed order calculations tend to go higher. So for the processes we're discussing today, in fact, these are all can be calculated next to leading order in QCD. And you also get various levels of resummation. And then, of course, in the Monte Carlos, you then have parton shower and underlying event to add extra jettiness and so on. And a resummation also sort of accounts for some of that effect in a fixed order calculation. So why WZ and WZ plus Jet production for the PDFs? Well, this is slightly covered already, and I think everyone in this audience probably knows well that this is the simplest hard scattering process to calculate at the LHC. when you look at the inclusive diagram, and gives you sensitivity to the quark PDFs in the leading order sort of picture, times the matrix element, times their Bjorken X and Q squared, times the phase space. And so when they're on shell, your Q squared is around the mass of the boson squared, and at rest you have a clear relationship with similar X for the X. And then, as Thomas has just shown us, if you go very forward, then you can, as forward as LHCb, then you can really sample simultaneously higher X and lower X for the same Q squared. What's maybe more interesting in terms of these data sets is the different flavor sensitivity that you're getting from these processes. So the Z boson is summing over the pairs of all flavors, UU bar, DD bar, and so on, times either the AM couplings or the weak couplings or the interference between them. And then W plus is sort of summing over pairs of positive, and W minus is summing over pairs of negatively charged quarks and antiquarks. So this gives you extra flavor sensitivity. If you fit them all simultaneously, then you can gain the kind of extra benefits that in precision that Thomas is alluding to from ratios and so on, because they automatically have to be fitted in the same time. Okay, if we look at the just on the usual kinematic plane, this is similar to what Thomas just showed. So you can see the hero region in the bottom right, and then these little bands show you basically what's probed by inclusive W and Z. And so it's generally higher. This is run 1 kinematic plane, which is what we actually use for our measurements. And in 13 TV, we would be at lower X. But you can see in the central band, we're probing a sort of region that was probed in X by Hera, but at much higher Q squared. And there's some small region of overlap. And yes, LHCb goes much further in X because they go into this range here where this rapidity shows you like the 4th bin. And of course, I think people know well that these are one of these James Stirling's original kind of conceits of plot. So why add the V plus jets? So if you look at just the W plus jets and you look on the right at the leading order diagram, you can see that you need in general more energy, so you'll get a higher Q squared to get your final state, and also higher X therefore to provide the center of mass energy. And of course you've got a gluon now, not just a quark in this case. The sensitivity there comes already. And yes, this previously in the inclusive case, its diagrams more like the bottom left one, which is one of the next leading order corrections to the W jets, I guess. And you can see that you get that's where you would get sensitivity indirectly to the gluon before. And of course, you still got your QQ bar type processes. So we have measurements, which is another reason to include this data. And so we have the 8 TV measurements of vector boson plus jets, which is really good statistics. So these were published in early 2018 and in 2019. And here I show on the right just an example of W plus jets compared to various predictions. And if you just look in the uppermost of the ratio panels, this is comparing the ratio of the data to MCFM predictions with some different PDF sets, and you can see that there's variation in the predictions from the different PDF sets. And we have next to leading order calculations for vector boson plus 1 jets, then Jetty, and so it's possible to put these into an NLO PDF fit. Okay, so how do we do that? So our fit is taking, as I said earlier, the combined Hera data with a Q squared above 10 GeV squared, and then the Atlas inclusive 7 TV W and Z production measurements, and then also the 8 TV vector boson plus jets data sets that I already mentioned, and particularly using the PTW distribution for W plus jets and double differential PT jet rapidity as jet cross sections for Z plus jets. And we use the open source XFitter package to do the QCD fit and extract the PDFs, as we've used always for Atlas fits. And we're expecting to see that the vector plus jets data will help constrain the high X quark and antiquark gluons, and possibly also the gluon. And so for this analysis, we produced 2 new atlas fits. One I'll just call, the upper one here, just call VJet20 most of the time. That's the new fit, including all this data. Then we've got WZ20, which is not including the W and Z plus jets. So that has a feature, as did the older atlas fit WZ16, of a higher unsuppressed strange, as Sasha already mentioned in his talk. And just with respect, we've done this so that it's got the same parameterization and so on as WZ20 as VJet20. Whereas the older fit had a slightly different parameterization and used a slightly different data set, so a different cut, for example, and just different treatment of the inclusive data. And so just so you can see that we can eliminate effects just from the changing of parameterization and really study the effect that you gain from including the vector boson plus jets data. So here are the fit assumptions and procedure. So these are fairly standard in atlas fits. So we have our ansatz of the PDFs as a function of x at the starting scale, which is 1.9 GeV squared. And then we parameterize the up valence, down valence, d bar, u bar, strange, and gluon. And we make some assumptions that give sensible behavior of various parts, which are given there. And then we fit the parameters and evolve to the scales, calculate the corresponding theory cross sections, and do the fit. And compared to our old fit, we essentially added this new DGX term, which is highlighted in red, which gives a bit more flexibility to the gluon. Okay. So how does the fit do? So first, here's the W plus jets data. So if you look at the fits without the data included, so the WZ20, you've got the red line is the PDF, and then the dashed red line shows the effect when you add shifts from the systematics that are nuisance parameters in the fit. And you can see that there's a tendency for this to fall off at high PT of the W, especially in the W plus data, but also in the W minus. And then when we include the data in the fit, that the central fit already increases at the shift. There's also still a bit of a shift needed to follow up to higher PT, the distribution. And then it falls off at the very highest spins, but you can see there's less of a shift in the nuisance parameters. And the starting point before shifting the nuisance parameters is much, much improved. Okay. If we look at the Z plus jets data, which is much more differential, of course, what you see here comparing, and I should have mentioned before, the yellow band is the total experimental uncertainty on the measurements. Then you can see here the shifts tend to be relatively uniform over the distributions, as you see, and small in the central value, and then the parameter, the central values tend to be higher of the fit, but then the nuisance parameter fits shift slightly higher and bring them to more or less the same level of agreement with the data. Maybe here in these higher bins, you see where the blue can do better sometimes or worse, depending on the bin. So there's some small difference, but over most of the Z plus jets change, there's not a big difference in the predictions from the fits. The overall quality is good for the fit, so there's 1.4 over 1.2 basically for chi-squared over number of degrees of freedom, and you can see in particular that the partial q-squared for the W plus jets, the partial chi-squared, sorry, for the W plus jets is a bit less than 1, and it's a bit over 1 for Z plus jets. So okay, and this fitting is pretty good, and there's the usual expression that we use for the chi-squared below, and in this case we take into account some statistical correlations in the V plus jets data that we don't need to do in the others. Okay, so what does this look like in terms of the actual effects? So in general, for this set of data, the valence is better determined than the down valence, so the up valence, and this you kind of expect just by having the HERA data in. So vector boson plus jets data has a larger effect on the down valence. You can see it on the right, it moves it down and towards the kind of results that global fitters tend to see. Then maybe more interestingly, if you look at the U bar, it doesn't change too much, but the D bar has quite a large pull at higher X. It's gone up, and the uncertainty is reduced quite a lot, as you can see. And then if we look on the next slide at the strange on the left, that has gone down and the uncertainty is reduced, although it's maxed a bit in the ratio plot because the absolute value is decreased. And also, if you look at the gluon in this higher X region, it's also reducing from coming from this data. Central value it's not as large a shift in general. So this actually is an interesting feature. This strange, this fall in the strange and the increase in the up, essentially partly compensates. If you look at the sums of the down type quarks, you can see that they're much more similar to each other than between the with and without WZ jets than the previous than the fits than the individual components. Okay, and then okay, so this fall in S and an increase in D will instantly be screaming to you that there must now be a bit more strangeness suppression in these fits than in the previous fits, and you'd be right to think that. So if you look in the top left here, we look at the usual RS ratio of the strange over the down and D bar and up bar, and what you can see here is the new WZ fit here, the blue, it's falling down a lot more, and this uncertainty is much smaller than in the fit, which is just using the inclusive data, which still favors this higher unsuppressed strange, but has very large uncertainties from the parameterization uncertainty. So they're basically compatible with each other, but clearly when you actually include the subset data, it's having an effect. And this is kind of consistent with the picture from W plus charm that CMS studies have shown before. And yeah, okay, on the right, this is just breaking down our uncertainties of our fit on this RS, and you can see there's a large component for the parameterization, and that's falling a bit in the tail there. Okay. If you want to look at something else, which is an interesting output of this, then you might be interested to look at the differences between D and U and down bar and U bar. And indeed, we look at the difference between down bar and U bar, and what you can get there. And this is coming from the plus, mostly from the difference between W plus and W minus jets. You can see that you can see a difference here. There's been now a tendency for our PDF to favor a positive value of D bar minus U bar above X of, well, 0.1, 0.2 is clear there. And this is a feature that global fits also tend to show, and this historically has come from fitting fixed target data, so it's interesting to see this as a non-fixed target set of data that favors this kind of behavior. Okay, and then just commenting a bit more then on comparisons to some global fits, which I mentioned. So here, if we look at some different global fits distributions, you have on the left versus CT18 and ABMP, and then the right versus MHT and then NPDF. You can see that this Atlas central value of the Atlas fit has still got a more unsuppressed strange or a less suppressed strange distribution at the low X, but then it falls down, whereas previously it would be staying higher across X. So it's more compatible. And if you look at the specific region, say of X of 0.023 here, it's chosen as this sort of interesting region about here, you can see that the Atlas VJet fit is here. All right, this value, yeah, that's great, yeah. And there's you can see that it's shifted left by adding, it's shifted to less suppressed by adding this data, and it's bringing it closer to the global fits, though still a bit higher. And if you also look a bit more at this plot here, I've actually gone to the scale of the Z boson. You can see that, say, also CT18A, which is included this same Atlas data set, tends to lie a bit higher than the others, and less suppressed strange as well. Okay. If we look at the DU and compared to some global fits, you can see that there's a difference in behavior, right, at the highest X, but it's consistent up to about 0.1 now, the Atlas fit, which is interesting. And okay, this is where the V plus jets is sensitive, and it's got some different behavior that's visible there. So that's going to be interesting to follow up on. So in summary, the progress in theory and recent measurements meant we can include vector boson plus jets data in next to next leading order PDF fits with Atlas, and we've shown that the data has the power to constrain mid to high XT and S-quark distributions, and also a bit on the gluon. The results show that including this data includes a consistency of fits to HERA plus Atlas data with global fits that also include, for example, fixed target data. And this falling RS distribution that we now see we now see is different to what we saw before, and also this XD minus XU positivity at high X is also something we didn't have before with our fits, and we still have this unsuppressed strange though at the lower X. Thank you.
Thanks very much, James, for this nice presentation. I'm opening floor for discussion. I see that Pavel already has raised hand. Please, Pavel.
Yes, well, first of all, I'm very happy to see that this new V plus jet data is analyzed, and hopefully it will be soon available for the other global analysis. Now, I have a question that would like to pick your mind on the following issue. Can you please go on to slide 14? So if you look at the total chi-squared after you include these new experiments, so the total chi-square per number of points actually went up after you include these experiments compared to the HERA fit only fit. And yet you are still using the delta chi-squared criterion for the experimental uncertainty, which results in very small PDF uncertainties. The question to you is, how do you reconcile these two observations? So in principle, I would hope that the chi-squared must be much closer to the number of points if you wish to use the delta chi-squared equal 1 criterion.
Yeah, it's a good question, and this is the way we've done it so far, and I think we have discussed and considered it in Atlas whether we might want to have a larger increase in chi-squared, and one could consider it, but I don't think we've done studies with any public results up to now. There are other people from Atlas who may know if we have anything more we can say on that at the moment, who are joined in the session.
It would be nice to understand it on your so obviously this is an important question for quantifying uncertainty on this issue.
Yes.
PDF.
Yeah, and you can see that the experimental is generally one of the smaller uncertainties as well, of course. So yes, so it's an interesting question too.
Thank you.
To look at more.
Okay, Mandy.
Actually, my comment is to Pavel as much as to James. We're thinking about it, Pavel. I don't think I can say anything more in public than that. Right?
I mean, we are thinking about it. It's enough, I guess, right?
You can add a modifier. We're thinking hard about it.
Yes, right. Quite right.
Thank you so much.
Okay, Robert.
Hi, so I think it's the first time I've seen your results, including the Z plus jets. The W plus jets have been around for a while. Now we fit the ZPT that I assume is a very overlapping data set. So could you just sort of confirm that and say what you think the benefits of one as opposed to the other are?
Good question. So this is so you're fitting the ZPT like the one that Sasha was discussing. Is that right?
Yeah,
that's also ATV. It will overlap. Of course, we have here the double differential with the jets. And so we chose it also for consistency with the W plus jets in the fit, of course. I'm trying to think what you would gain. Of course, you're with a higher scale jet.
I appreciate this. This may need some thinking about.
Yeah, it's a thing. There could be overlap, and we would have to think about as well. Yeah, in terms of if you wanted to include both sets, it would have to be looked at.
Well, I actually asked about this in a talk yesterday about the Z plus jets, and was told that the statistical correlations were not really available to make that possible.
Yeah, and I think that's likely to stay the case. But this is something we should discuss. So we are currently, I mean, as it's mentioned in our abstract, so I'm allowed to say that we're working on a global fit with many different data sets. So there we will have at least looked carefully at what the best we can say about the overlaps of our various data sets that can be fitted. But yes, I think it will be hard to get something with precise correlation, so it may be a case of choosing one or the other to include.
Okay, I don't see any more hands. Anybody else wants to ask a question? Very good, then we will move to the last talk of this session today. And Tom Cridge will tell us about benchmarking of global PDF fits. And we are only 5 minutes behind. This is the last talk, so I will not count time. I hope, Tom, that you will not disappoint me and will keep reasonably within time. So please share your slides and start.
Sorry, 1 second.
We still cannot see the slides.
Yeah, I know. I'm trying to share them, but it's not allowing me to at the minute, I'm afraid.
Okay, let me pull them out just in case, and maybe I can share if you don't manage.
Yeah, perhaps that's easier. Just you do it. That's to avoid any time wasting.
Let me try to get them in the. No. I would like to take them in the full screen. Oh.
Do you have them? If not, I can try leave and rejoin to see if that
helps. No, well, I could do it now, I think.
Okay, go ahead then. That'll avoid us wasting any time.
Can you see the slides?
Yes, I can. Thank you.
Very good. So you need to tell me to change the page.
Yes, sure. Thank you. Okay, well, thanks for the introduction. I'm going to talk to you about the PDF4LHC21 benchmarking exercise that we've been doing. This is obviously work on behalf of many different people, both in the 3 main global PDF that's involved, MSHC, CTNN, and PDF, and also outside that, so thank you to everybody. As for a brief outline of the talk, I think you can see that on the slides now. I'm going to necessarily have to go through quite quickly through some of this, so please ask questions at the end. I'm also happy to discuss various points, but essentially what I'm going to do is briefly motivate the need for this PDF benchmarking, discuss our aims in terms of understanding the origins of the differences between the 3 different global fits, discuss our approach. In particular, relevant for that is the use of these so-called reduced fits, whereby we're fitting a small subset of the data sets that usually go in the global fits to allow us to compare the 3 groups against one another more straightforwardly for the benchmarking. I'll briefly show how these reduced fits compare to the global fits so that you can sort of get a handle on what they look like. I'll then move on to the actual benchmarking itself, which will involve comparing these reduced fits against one another in terms of the PDFs, in terms of the chi-squareds. I'll then briefly, towards the end, look at 2 of the areas of difference that we've been examining in the benchmarking, and these are in terms of the flavor decomposition and the strangeness. That's relevant in particular for the NUTEV data treatment, and also the Hayek-Gluon region, which is of obvious relevance for the global PDF fits. And so far, we've been focusing on benchmarking the Atlas TT bar data here. I'll then conclude and show some luminosity comparisons as well. So if we move on to the next slide, please. Okay, so just as a very brief introduction, here we have plots for the gluon with the uncertainties at the top and the central values at the bottom here. On the left, you have the PDFs at the status of PDF4LHC15. So essentially PDF4LHC15 was carried out more than 5 years ago now, and a lot of things have changed. There have been many new data sets added to the PDFs, been many theoretical improvements, N and LO and the like. And as a result, we now know the PDFs more accurately and precisely than ever before, but there are some differences emerging. So in terms of, if we look at the uncertainties here, at the top we have the PDFs as they stood PDF4LHC15, that's CT14, MHT14, and then in PDF 3.0. And if you compare that to the the most recent PDF sets on the right, MSHT20, NMPDF3.1, and CT18A, where I've chosen A here because it includes the Atlas 7TV WZ data. You can see that there's been a general reduction in the PDF uncertainties, which obviously are very good and reassuring. It wasn't necessarily guaranteed a priori because of things like dataset tensions and extended parameterizations and the like. On the other hand, if you look at the bottom here in terms of the central values, the agreement is no longer as good. There are some differences starting to emerge between the three groups. And we really want to try and understand these differences through this benchmarking exercise. So if we move to the next slide. Great, yeah, so essentially we want to try and benchmark these differences so that we can understand the differences in the global fits, because we need to do this ahead of a new PDF4LHC future combination, a PDF4LHC21 combination set of PDFs. What we need to do is to try and understand the origin of the differences here. That means, are they due to things like the variations of the experimental input, different theory settings, different methodologies? And that's our aim, and our approach here is to essentially seek to remove as many of these differences in input as possible. And that means taking a common input data set, a small subset of the data sets fitted by the global fits, taking common theory settings wherever possible, and examining methodological differences in parallel as much as possible. And these then allow us to remove these differences so that in the benchmarking we can examine remaining differences in these so-called reduced fits. These reduced fits then offer us essentially an ease of comparison between the global fits, albeit at the expense of the usual robustness you get from the fitting the full data sets of the global fit PDFs. To benchmark the PDF reduced fits against one another, you then have three main levers, if you like. You can compare the PDFs directly against one another to look for areas of difference. You can also compare the chi-squareds against one another to look for particular data sets which are showing differences, which may give you a handle on where these differences are arising. And if you need finer detail still, you can compare the cross sections against one another and point-by-point theory predictions. And in the coming slides, I'll show some examples of doing all three of those things. So if we move to the next slide. So here, I'm just giving you some more information on the reduced fit data set that we've chosen to use. As I've mentioned now, we're choosing a small subset of data sets that's fit by all three groups, that's MSHT, CT, and NMPDF, in almost exactly the same way. And when you look at this, you notice the list is actually surprisingly small because of various subtleties in treating the different data sets involved. On top of that, you then take the most conservative cuts applied by any group for consistency. And you must also in parallel ensure that you have enough data sets and a sufficient variety of data set types of fit so that you have some constraints on all the PDF flavors. Of course, the constraints are less than the global fits. I've given you here briefly at the bottom an overall list of the reduced fit data sets. I'm not going to go into any detail on this here because of time, but you can see there's still a variety of data sets from the older fixed target and DIS data sets through the HERA combined data through to the more recent LHC data, including the Atlas 7TV WZ data and the CMS 8TV inclusive JET data, the latter of which, of course, giving you constraints on the highest gluon. So if we move on, the other thing that we have to ensure is the same between the various fits is the theory settings. By choosing common theory settings wherever possible for simplicity, we remove this potential source of difference for the benchmarking. That means choosing the same heavy quark masses, the same alpha S value, setting no strangeness asymmetry at the input scale, choosing a perturbative charm, which is of course of relevance for NMPDF, choosing positive definite quark distributions, having no neutron or nuclear corrections, because that's another potential source of difference between the three groups. And there are a few other things as well. And I should note at this stage that not only the reduced fit data sets, but also these common theory settings, they're not the chosen settings for any one group, but they're rather a compromise to the least common denominator in each case. And so we really wouldn't recommend them for a global fit, but they are very useful for this benchmarking. So if we move on. So you may ask, well, what do these reduced fits look like and how do they compare to the global fits? So very quickly here, I'm going to show that for the three different groups, beginning here with the CT18 reduced fit in red relative to their global fit, albeit the CT18A global fit because of the inclusion of the 7TVWZ data in gray. And what you see is there's generally good compatibility between the reduced and the global fits, with some increases in the U-bar in the bottom right, signaling a flavor decomposition difference, and also changes in the highest gluon shape in the top left. If you move on to the next slide, we also see the uncertainty comparison for the CT18 reduced fit. You can see here there's some increase in the nominal PDF uncertainties from the global fit to the reduced fit, particularly at low X. Moving on, you see the same comparison for NMPDF 3.1 with their reduced fit in green relative to their global fit in gray. Again, there's a good overall compatibility. There's some changes in the Hayek's gluon shape in the top left again. That's due to the removal of the top data and the addition of the CMS8TV jet data relative to the PDF 3.1 global fit. There's also some changes perhaps in flavor decomposition, and you can notice there are some changes in the strangeness, which I'll refer to later with relevance to the NUTEP data. So moving on again, you can see the NMPDF 3.1 uncertainties for the reduced fit relative to the global fit. Again, there's generally slightly increased uncertainties, particularly for the gluon, for example. Finally, the same comparison for MSHT is on this slide now. You can see the MSHT20 reduced fit in blue relative to the global fit in gray. Again, we're seeing good compatibility. There are changes in the flavor decomposition, for example, in the U-bar in the bottom right. There are changes in the Hayek's gluon shape in the top left. And in the bottom left here, we're also seeing changes in the strangeness. That's an expected and understood difference. Essentially, the MSHT20 global fit includes this 8TV Atlas WZ data, which we know increases the strangeness, whereas this is removed from the reduced fit. Finally, looking at the uncertainties for MSHT20, you can see there's a more marked increase in the uncertainties from the global fit to the reduced fit for MSHT20. That's particularly and specifically outside of the regions where there are data constraints for those reduced fits. So, for example, in the low X regions. Of course, what you actually want to do is what I'll show on the next slide, which is the actual comparison of the reduced fits against one another. That's what you want to do for the benchmarking. And this is the current status of this comparison. What you can see is there's generally very good agreement with uncertainties, particularly if you take the gluon in the top left, the reduced fits are in very good agreement between the three groups. Perhaps an exception to this is if you look in the bottom right for the U-bar, the NMPDF 3.1 reduced fit U-bar in green is slightly lower than the others, perhaps showing some Hayek's flavor decomposition difference remaining. Also in the bottom left, you can see the NMPDF 3.1 strangeness is perhaps slightly higher than the other groups in the 10 to the minus 2, 10 to the minus 1 region, but within uncertainties. But I'm going to reference that later when I discuss the NUTEP data treatment. So if we move on to the next slide, you can see the uncertainty comparison. Basically, you see very similar size uncertainties in the data regions for the reduced fits. That's obviously very reassuring. MSHT generally have larger uncertainties in the regions where there aren't constraints in this reduced fit, so the low X, for example. And there is a parallel study ongoing into the differences in the uncertainty bands, but I'm not going to reference this further here because of time. So if we move on to the next slide, what I'm now going to show you is actually chi-squared comparisons for the different reduced fits. Before you actually compare those after fitting, the sensible thing to do is to use the three groups reduced fits and to make predictions with a fixed input PDF. So take the PDF for LHC15 PDFs as input and calculate the chi-squareds in the three groups. And that allows you to identify any differences in theory or data between the groups before you actually perform the fit themselves. And I'm not going to go into too much detail on this, but if you look down the various data sets that are in this table, you see there's generally pretty good agreement between the different groups. There are some exceptions. One obvious one here is the hero, which is the fifth from the top. NMPDF has a notably larger chi-squared over N here, but that's an understood difference. It's essentially due to a flavor scheme mismatch between the PDF from LHC15 and NMPDF. And that then, because that's over half the reduced data set, that then causes the difference in the chi-squared over N for the overall fit quality. But if you move on to the next slide, you can see the chi-squareds over N for the actual reduced fits themselves. First of all, you can see this hero difference is removed. So that shows you we understand that effect. But overall, if you go to the bottom of the table here, you can see there's a similar overall fit quality in chi-squared over N for the reduced fits of the three groups. CT obtaining 1.14, MSHT 1.15, and then PDF 1.2. So this is, you're getting very similar behavior. On the level of the individual data sets, there are perhaps some slight differences. If you look at the NUTEF, for example, which is fourth from the top, CT and MSHT are obtaining 0.8, whereas NMPDF is obtaining 1.2. What that's really doing is reflecting the larger strangeness that we saw in the NMPDF reduced fit earlier. There are perhaps some other further differences. The only one that I want to briefly point out here is that there are some differences in the NMPDF fit quality to small data sets. Take, for example, the third from bottom, the CMS70V electron asymmetry with just 11 points. CT and MSHT are fitting that with around 1.5 per point, whereas NMPDF is obtaining half that, 0.76. And I'll give a potential explanation for that later. So moving on, I now want to discuss some of the specific differences that we've seen in the reduced fits in the benchmarking and how we've understood them over the past few months. One of the main differences between the first reduced sets was in the flavor decomposition and particularly the strangeness. And it turns out the NUTEP dimuon data is a key driver of this. Part of the reason for this is simply that it's a complicated data set. It requires knowledge not only of the charm to hadrons branching ratio, but also treatment of the non-isoscalarity of the target, acceptance corrections, and a variety of other things. And essentially, these are all areas where the different groups can do different things, and that's where you end up with different behavior. The one that's of particular relevance is this charm to hadrons branching ratio, and that's because, as you can see in the plot in the bottom right, essentially it's anti-correlated with total strangeness. A larger branching ratio here means that to fit the same dimuon data, you need a smaller total strangeness. And the three different groups have different values for this branching ratio, and that's therefore going to have a knock-on effect for the strangeness for the reduced fits. If you move on to the next slide, you can see that after setting all these various things the same, in particular choosing the same dimuon branching ratio and fixing it at this 0.092 value, in the plot on the right, you can see the agreement of the strangeness is much improved, with the various groups are now largely in agreement within the data region within uncertainties. Because we're in a reduced fit, this increased agreement of the strangeness then also has a knock-on effect to reduce the flavor decomposition differences as well. Moving on, however, because of time, I want to talk to you about the Hayek's gluon. This is obviously a region of interest for the global fits, as we've heard over the past couple of days. And there are three main data sets playing a role here, or data set types. You have jet data, top data, and ZPT data. And in the plot here, you can see that these have different poles on the MSHT20 gluon. Not only that, but various of these data sets are not straightforward to fit. You can have difficulties fitting all of the bins, possible tensions between these data sets or between these data sets and other global fit data sets, and issues of correlated systematics. And the latter of these is an issue that's particularly been pointed out in the last couple of days by various of the groups. And so what we want to understand for this benchmarking is, given the three groups observe differences in the relative importance of these data sets and in the quality of their individual fits, can we understand this better in the reduced fits? And can we understand this in the benchmarking? So moving on to the next slide, the data set that we've chosen to focus on first is the Atlas 8TV multi-differential TT bar lepton plus jet data set. For those of you who haven't been following this story, essentially this data comes differential in 4 different variables with statistical and systematic correlations included. And that means that theoretically you can fit all these 4 distributions simultaneously. In reality, what's been observed is that MSHT and CT find difficulties in fitting all these distributions simultaneously. You get a very poor fit. At the same time, MSHT, CT, and even Atlas have found that you cannot actually get a very good fit to the rapidity distributions even when fit individually. In contrast, NMPDF 3.0, which didn't have lots of the other jet data that's since been included, however, found they were able to fit all 4 distributions well individually. So we want to understand this in the context of the benchmarking. So what we've done is we've started by adding this data set to the reduced fits that we now have a relatively good agreement for, and first making predictions with PDF4LHC read in. Without fitting, you can check that the data in theory are in agreement, and you can also look at the chi-squareds for the 3 different groups in the table here. And what you see is the chi-squareds are in agreement between all 3 groups, and moreover, they're following the global fit pattern seen by MSHT and CT, whereby the PT and MTT distributions, the first and last rows here, can be well fit, but the rapidity distributions are poorly fit. And what this tells you, and that's even true of NMPDF here, you can see. And what this tells you is that the differences in the global fits are likely not down to different TT bar theory implementations. So you can ask, well, what are they down to? So if you move on to the next slide, you can see what happens when these are included in the reduced fit. There's lots of information on here, but for interest of time, just focus on the first 3 rows in this table here. What that essentially shows you is that once we actually fit these in the reduced fits, MSHT and CT are seeing the same pattern as before, the same as their global fits, where the rapidities can still not be fit well, perhaps marginally better fit than the global fits, but still fit poorly. On the other hand, NMPDF are already at this stage able to fit the rapidity distributions well. So the same pattern is emerging in the reduced fits. So if you move on to the next slide, we've had some discussions at perhaps trying to explain this, and this is very much preliminary. One potential explanation for this is that does it lie in other data sets included in potential tensions? We heard yesterday that NMPDF 4.0 will have much more of this jet data included. That has an effect on the Hayek's gluon, and it sees similar issues to MSHT, CT, and Atlas for this data set. So therefore, it's going to be useful for us to consider different jet data sets, as well as or instead of the CMS8TV jets that's been included in the reduced fits. However, there is a potential further explanation that we've discovered in the process of this benchmarking. And briefly, that's the division between training and validation data for NMPDF. Essentially, they typically divide a data set 50-50 between training and validation. But of course, for small data sets, of which the Atlas TT bar is an example, this division is just unfeasible. For example, there are 5 points for the rapidity distributions. So all the data therefore has to go into the training. What this is doing potentially is double weighting, or at least up weighting, these smaller data sets. And so you're going to get a better fit to those, perhaps at the expense of fits to larger data sets. And so what we've done in the context of these reduced fits is take the MSHT and NMPDF reduced fits in the first two columns here, and then in the third column perform an MSHT reduced fit, but double weighting some of these smaller data sets in the light blue. And what you can see is this does have an impact on some of the fit qualities. Take the CMSW asymmetry, which I pointed out earlier. Clearly, between the first and third columns, there's a notable improvement in the chi-squared/n for MSHT by double weighting this. Moreover, and more markedly, looking at the rapidity distributions, you can see that you go from not being able to fit these very well in chi-squared/n to being able to fit them now reasonably, and certainly in the direction of NMPDF. So perhaps this is an explanation of some of these effects, and that's something we want to look into further. In any case, I know the time is short, so let's move on and I'll come towards my conclusions. Before I do so, I just briefly wanted to very quickly show a luminosity comparison of these reduced fits. You can see in the top left here, the gluon-gluon luminosity for these three groups reduced fits are in very good agreement. And the same holds for quark and quark-gluon. For the quark-antiquark in the top right, there are perhaps some slight differences in the NMPDF 3.1, which is, albeit just about within uncertainties, which perhaps is related to remaining flavor decomposition differences that we should look further into. So moving on to the last slide, which is just the conclusion slide. I'm not going to go through all this, but essentially we've seen that using these reduced fits and reduced data sets gives us a good handle on being able to understand the differences in the global fits. We've now got a good overall consistency between the reduced fits of the various different groups, particularly in the luminosities. And this benchmarking has enabled us to understand many of these differences, for example, in the strangeness, and we're also continually looking at the highest gluon region of interest now. Some differences are still remaining, but many of these are outside of the data regions. So in terms of our future direction of work, we want to continue to analyze the highest gluon and more generally just expand our reduced fits that we now have a good handle on towards the global fits to understand remaining differences. So thank you, everyone. Once we've done all this, of course, we can then consider a PDF4LHC21 combination set. So thank you, and let me know if you have any questions.
Thanks a lot, Tom. I must say I'm really impressed. This is huge congratulations to the three groups for this effort. This looks very nice. And I see that Simona has a question already, so please start.
Yes, thanks, Tom, for the talk. I had a question in this table of chi-square comparisons.
Okay.
Maybe I missed and you explained it, but I was just trying to understand where this may come from in the sense.
Which slide are you looking at in particular?
Sorry, yeah, you have many. No, the one where you actually try to compare, I think, the reduced fit chi-squares, and you said that for certain data sets, you still see different chi-squares, like the Atlas data. I think the next slide, maybe.
The next one, yes, is after fitting. Yeah.
Yeah. So if you have any idea for why, for example, these Atlas data may have these differences.
Yes, so there are some data sets here which I didn't go into, and the Atlas and the LHCb are two examples where there are still some slight remaining differences. And that's something we definitely want to look into. Perhaps it's related to some of these remaining differences in the PDFs themselves. One thing that is potentially an option, and which we are, want to look into at the current time, is it seems that perhaps some of this double weighting could play a role. But also, in general, we just need to look further into this. This is one of the remaining differences that we want to look into for the reduced sets. But certainly, these differences were much smaller than the differences we were seeing in the directions that we've looked so far. But this is something we do need to look into further. I agree.
So maybe a quick follow-up question then. So, but in these fits, are you using the same theory predictions and say? So I guess the chi-square definition is also the same.
Yeah, we have looked into a few of these issues. We've mainly looked into the data sets I've considered. In terms of the theory predictions, what we can do is compare the PDF4LHC comparisons, right? Because that tells you the theory data comparisons directly themselves. And that's usually the first point we do when we're looking at a particular data set. We haven't directly done that yet for the Atlas and LHCb because it's not one of the data sets we saw the biggest differences, so we haven't focused upon it. But what you can see in the last table is that you're seeing similar chi-squareds over n before the fit. And the differences are sort of remaining after the fit. So we don't expect that to be the source of the differences, but we really would need to look into that further. And that's something I agree we should do.
Thanks.
Okay, we have more questions. First was Joey, please.
Yes, it's a comment more than a question. If you can go to the slide where you compared the PDF luminosities and their uncertainties for the three global fits.
Where was the slide? I'm sorry.
23 probably.
23?
Probably, yes.
Well, this is for CT18 or 18A.
This one?
No, not for the reduced fits, but for the full global fits.
Ah, so you don't mean the
That-
luminosities, you mean the gluon. That's at the beginning.
Right, so that's in the beginning. I thought it was the luminosity, but maybe I was wrong.
Here?
No, a couple of slides before, I'm afraid, about 4 roughly. Yes, here, presumably.
Yes, okay, so if you look on the right-hand side, you'll notice that there is a spread between the 3 predictions for the gluon distributions, and that will translate, of course, into the glue PDF luminosity. This is just an indication of the difficulty, I think, of doing a global PDF fit, that adding more data does not necessarily lead to a decrease in uncertainty. In this sense here, that the ultimate combination of these 3 PDFs, or rather CT18 rather than CT18A, but it would look almost identical to what you've shown here, is going to have an appreciable contribution from the spread of the central values. That's something we didn't have for PDF for LHC15. And again, at the time of PDF for LHC15, I said this could be just a lucky accident, and we may not see that in a future combination. And indeed, we don't. And just to add some more confusion to the issue, that you've seen the neural net PDF 4.0, which is actually lies below either CT18 or MSHT20. So again, just wanted to point out, I always like to say that the path to precision PDFs goes through the data. Sometimes the data doesn't allow you to take the most direct path to get the greatest precision for the PDFs. And this appears to be, one of those cases.
Okay, thank you. I saw Pavel.
This is just to reply to Simone's question. So if you look at the chi-square for the Atlas WZ data, you see that there is a large uncertainty on the chi-square per number of points because the data are so precise. And so like the 68% PDF uncertainty translates in the change in chi-squared by 1 unit, roughly speaking, in the CT18 analysis. So therefore, these three feeds are really very compatible in their predictions for the Atlas 7 TV data, and so I don't think there is any disagreement. But of course, we can further fine-tune the theory predictions by using one PDF set, let's say PDF4LHC15, and there was another table, I believe, that shows how the chi-square changes as a result of the theory prediction only.
Yeah, the previous slide.
Yeah.
Yeah, so this is just showing that they're also seeing similar chi-squareds over n when you're reading the same input PDFs, which is telling you about the theory and data agreement in the different groups.
So obviously the treatment of electroweak corrections, for example, will be important here.
Sure, yes.
Yeah, so maybe this is where I was trying to go, Pavel. So I was trying to understand if you also synchronize, so not just the, say every flavor scheme, but also like your K-factors, electroweak for QCD, electroweak, and things like that. Not just for Atlas. I mean, you have this LHCb, which is also different. And
yeah, definitely. And I think that's already a pretty good agreement. And so we did put an effort, and I think Tom explained some of them to synchronize these predictions for this benchmarking study. However, of course, in the full calculation, so we do not want to synchronize everything because that's a measure of the additional uncertainty in fitting the data.
Yeah, no, of course.
Yeah, there's always a balance here between trying to get things exactly the same in the reduced fit, but also correctly reflecting the differences in the global fits.
Okay, are there any other questions? I didn't see any raised hands, but maybe somebody just wants to ask a question. Okay, I don't hear anybody. So thank you again, Tom. This was the last talk of the session today. So thank you everybody for participating, for very nice talks and very lively discussion. And again, thank to all the speakers for staying in time. And we meet tomorrow for our last session. Thank you very much.